Okay, good morning, everyone, and I'm Jie Chen. I'm a postdoc in UF. So I will introduce something about the InSAR application in permafrost region using MintPy and HyP3. I guess I maybe somebody do not have much backgrounds in permafrost. So let me introduce some basic concepts of the permafrost. So permafrost is solely defined by a temperature which is below 0 Celsius degree, which should be continually present for at least 2 years. So the right figure shows permafrost distribution in the northern hemisphere, which is occupied almost 24% of the entire land region. So it's a big portion of the ground. So where the active layer is the layer above the permafrost, which thaws in summer and freeze in winter. Let me I would like to show you some examples. So as you can see, there is a clear boundary between the active layer and the permafrost layer in both figures. And the left figure is from Tibetan Plateau. The right figure is from Siberia. And both the figures are the exposed ground. They have exposed ground ice. So in the left figure, if you see the permafrost layer, we cannot, it's difficult to tell if what's inside, but if you clean it off using water, you can see there is a almost pure ice in this layer. And in the red figure, I think it's a similar case, as we can see clear here it's a permafrost and it's pure, almost pure ground ice. So the next one is the next one is why ground deformation in permafrost region matters, because under the climate change or the climate extremes, the landscapes in permafrost region do have a lot of changes because of the temperature or the other surface processes. The figure shows, the first figure shows the active layer detachment, which is only the active layer is like a slump. It's detached along the permafrost table, and this is a source slump. You can see it's also it's because of the thawing over ice ridge or massive ground ice, and this is a landslide, which also occurs in permafrost region. We cannot say this is totally caused by permafrost variation, but we do believe that the permafrost, the freeze thaw processes may play a key, also an important role in the landslide. And you can also see in the permafrost regions, sometimes the road the road cracks, and which may cause some infrastructure problems. So of course, there is also another key components from permafrost is which is very hot, maybe recent years, is the permafrost carbon. There's a large amount of carbon stored in the permafrost layer, maybe, and once it is thawed, it may be released a large amount of carbon, or and provide maybe positive feedbacks to the climate warming. So we do think that quantifying permafrost ground deformation can help us to better understanding the permafrost variabilities in different scales. So this is a very simple illustration of how what is the permafrost ground deformation. So generally, I mean, in the winter season, the active layer is frozen. So when the summer comes, so the active layer will gradually thaw, and the ice in the active layer will transmit from ice to liquid water, and because of the volume change of ice and water, the ground will suffer from ground subsidence, and then in winter the thawed active layer will refrozen again, and causing the we can call it ground uplift or frost heave something. Yeah. So in general speaking, the ground deformation happening in the active layer is a seasonal subsidence. I mean, if there is no other disturbance, such as maybe the climatic extremes or the changes of soil moisture, ideally the seasonal subsidence will be like a periodical deformation. And once, I mean, some disturbance such as wildfire or climatic extremes, the permafrost will also, because of more energy flux penetrated into the permafrost, and the permafrost will thaw, on which will be cause deformation, irreversible deformation trend, which may be, or which mostly happen in the thaw season. So in this case, I mean, we can use in two terms to determine the to represent the permafrost ground deformation, which is the seasonal subsidence and the deformation trends, which generally we can use in a step-wise function, or just using linear function. So here's a simple examples in Tibetan Plateau. So yeah, you can see the left figure the left figure shows the linear subsidence trend, and the right figure shows the season deformation. We can see there a spatial pattern is very different, and also the magnitude is also very different. And so with the InSAR time series and the model I showed in the previous slide, we can estimate the subsidence trend and the season subsidence, which you can see here. The subsidence trend in this point 1 here is very large, and up to 80 millimeters. So this is a example how the permafrost ground deformation looks like. So the next one is I would like to show you some the notebooks here. Maybe so first we can go to the workshop Jupyter books, and then go to NISAR and the Jupyter books. You can see here the HyP3. Yeah, and this one. Yes, yeah, it's this one. I will show you some how to download, how to order the int programs from HyP3. Especially designed, especially for permafrost applications. Here, yeah, as we can first restart and clean our cells. So you can it will not take a long time. So you can run step one by one. Try. So here I provide all the parameters and the folders. Here's for example, here's the project name, and where we can download the InSAR data, and the start and end data is I used the 2 years data, and the maximum temporal baseline here for the adjacent interconnections is 36 days. But this, I mean, is a bit different from other InSAR applications. It's because we don't have much. We didn't have I mean, valid intergrams in the winter season because was a heavy snow cover in Arctic permafrost regions. So we have to, if we want to see the interannual changes of permafrost ground deformation, how to use in the interannual interconnections. So I will show you. This is, I mean, the AOI regions I use here. Here I provide the UTM projection. This is because the programs we downloaded, we converted to the UTM, and but in the ASF vertex, we are still using the longitude and latitude. Maybe we can show you a bit using the ASF download and to show. Yeah, you can see. Yeah, here I redefined some. I mean, to maybe the seasonal for January 1st to the October 1st, and yeah, we can see listed. There are 21 SLC images. So if we go to, oh, it's not, it's sparse research. No, is this one? Oh, sorry. Oh, I forgot. Where is it?
Are you looking for the?
Oh, this here. It's sorry. Yeah. Okay, so because we cannot using the intergrams in winter season, so we have to refine it. I mean, like seasonal also here. October 1st is summer season. So you can see if you stretch it here, so you can see I mean the interannual the intergrams from different years, they are not connected. So we have to maybe we need to if we want to use this for permafrost study, we have to define some interannual pairs using HyP3, which is also very friendly, I think. And so you can I can show you how to do it here. So this is the same numbers of with ASF vertex. There are total 21 SLC images, and here is how we set the networks. And in the in the vertex, we can only set this into any for the I mean adjacent intergrams. Of course, if you want, you can also using the custom pairs to connect them. But here we try to using the HyP3 to simply to connect the interannual pairs using this threshold here. Is the interannual one is 350 and 380 days in between. So you can see here, so this is the signal interprograms. It's the same with these pairs. And then we also include some interlinear pairs to make the interlinear connection here. So the next is to just like Alex showed yesterday, is how to download the data. I'm not going to download the data here because it may take a long time. So after that, we can also just like Rudy said, maybe if you your study area is small, we can using this function to clip. This is can be used for the HyP3 interprogram products. And as OpenScienceLab do not have a large storage space, so I try to download one and crop one, so it will not took too much space. So let's go to the other.
And Jie, before you move on to the next notebook, there's just one question in the QA related to the previous notebook for ordering the data. And so Amrit Thapa asks, could you elaborate on the phase filter parameter that you defined in the notebook and how it influences interferogram generation and provide guidance on selecting the correct value?
Okay, influencing the. Okay, I'll undeployed. Yeah, I mean it really depends. I mean, because in permafrost regions, it's for the Sentinel-1 data, the decorrelation process is very fast, and so as we not focusing on the infrastructure, for example, so we do not care too much. I mean the very local scale, very local details. So sometimes for me, I to increase possibility to construct the internu connections. So I tend to using bit hair phase filter parameters. And this for this parameter, you can set it's on the, you can set here. I think it's yeah, it's here. You can also set this parameter. I mean, in the ASF vertex. Yes. So the next one is we can use in MintPy to deal with InSAR time series in permafrost region. Here's it's let me reopen it. It's in the ASF HyP3. The HyP3 data receives and click this one. Okay. So this this notebook is also written from Eric and modified by Alex and me. And so we can run step by step. This is for loading the packages we used in this notebook. And here is the data, because we are not ordering the data currently. So we store the data in Amazon so we can run it. So this is the similar things to set configure file name, and for this step is also the same with Eric's notebook. We can download the prepared data for this notebook. It will take several seconds. It will be fast because our AUI is relatively small. Maybe, and then okay, great. So I think maybe we can see, okay, it's in your home directory. That's InSAR sparse permafrost, this folder. So we will not. So if you not configure the CDS, you can configure it here or as well. So this is overview. Again, this is on. I mean, all the parameters I used in this specific notebook. So I mean, the InSAR processor we use in HyP3. We have to modify because the default one is S. So the network for construct the connections. This is the average spatial coherence, and we using the first data as reference data, and this is a reference point which I set in the bedrock regions. So the temporal coherence, yeah, and yeah, I mean in this example, because our region is relative is around 10 kilometers, so generally I think we do not need to do not need to perform the troposphere decay using the EIE file or the IPS. But I just to show you how to use it here. And so this is a bit different because in permafrost region that I showed in the presentation, there's not only maybe not only a linear deformation trend, but also a periodical deformation. Here for this yeah, this is the deformation model parameters. This is means the 1 year cycle. So we can run it. Okay, we already ran. Oh, sorry. I need to restart. Oh no, we do not need. Okay. So this is a configure file here, and create the configure file. So we can see the configure file. It's right here, and then it's we can load data. The interprograms are all downloaded. The cropped interprograms here are all here. You can see this shows the input informations. Here is sometimes, especially in permafrost region, we need to modify the networks because of sometimes they're really very low coherence. So let's see here, number in interprograms removed is 23, and the kept is 48. We can plot to see, I mean, the connections. So, I mean, still most of the interannual pairs will be excluded, but I mean, those sparse time series analyze if we keep several of the interannual ones, we can still I think we can still work on it. So this is to relocate the reference point we provide. So this is generally we did this step in we check the individual interprograms here to see if there is a very strong, I mean, phase unwrapping errors here. You can and then if there is, you can manually remove the interprograms from the configure view. There is a parameter you can find from the configure view. So the next one is reference information, and Then we do the inversion, the same one with Eric show. Yeah, here is I mean the retrieved InSAR deformation time series, which is the first one is reference, and here is the reference point. You can see I mean the seasonal subsidence in the late there is accumulated seasonal subsidence. It's from it's in the late September in these regions, and the second year is almost the same case. So here, but we also see this kind of still have some atmospheric errors. So we can try to perform the troposphere propagation decay correction, which I mean we already downloaded the data in this folder, so you don't have to download. And you of course you can download your own data, and then we can run step by step, and we can also show you what happens when we correct the atmospheric errors. Yeah, I mean, at least from this figure, there's a bit, it's a little bit, I mean, to the atmosphere was reduced, and then we conduct the normal, I mean, the step-by-step for the deramping on the correction, topographic phase correction. And then we can see the final InSAR time series over here. Also, yeah, you can see here after the atmospheric correction, you can see at least from the second images, there is a less atmospheric components here, and we can also see the better deformation patterns in the intergrams. But I mean, still it seems there are still some problems. It's kind of maybe related to the unwrapping error. I'm not going to serve this here. And we can also, I mean, because to check if there are strong errors, we can also calculate the it's like using this command to calculate the adjacent time series to calculate the temporal derivatives, which is like here. I can show you. Yeah, this one. You can see the adjacent. I mean the intergrams. There is no very strong differences between them, but there is a very large uplift in this data. This is because the connection between this intergram to the previous one is the ground suffers from the inter is suffering from the inter winter uplift, or we can call it winter heave. It's very strong signals here. It's as normal. We can also calculate the time series, the residuals, and yeah, this is also to if you want to choose another reference data, you can use this step to do it. And here we can the next step is we can using the permafrost model we mentioned. But I mean, in the MintPy, it's not the same one as I mentioned in the PowerPoint. Yeah, and in the MintPy, they using the sine cosine seasonal subsidence model. And we can run this step. And because I mean in the MintPy their amplitude, the seasonal amplitude is calculated is only half of the real subsidence seasonal subsidence. So here I using the image mice in MintPy to calculate the seasonal subsidence here. So the next step is we can I can show you the the velocities, and the other one is the seasonal subsidence here. But I mean, it's maybe it's not common even to me. I mean, in these 2 years, it seems no I mean no deformation trends, no subsidence trend, but mostly I mean the uplift trend. Yeah, but this I can explain it a bit. This is because in this region, in these 2 years, the climate is very cold, and this is also the reason why we can do the interannual connections. And in many cases, it's difficult to find even one interannual connections in at least in Alaska region. So this is also the reason why I pick up the 2 years as an illustration to show the interannual connections. And you can see also the seasonal subsidence is very it's also strong in permafrost regions, which we cannot ignore. So we can also make a plot of to see how good the fitness of the deformation models, such as you can see here's the fit of the using the seasonal subsidence and the linear subsidence trend. Yes. And this is also explained by Eric, how to quantify how to do the error analysis for the InSAR is almost the same ones. So you can see these are bedrocks, and the coherence, the spatial coherence is high, and this is maybe it's Drindelic basins, or even some karst landforms. They have low coherence, temporal coherence. The temporal coherence seems better than that one, and yeah, this is a velocity standard deviation. It's also, I mean, the similar. I mean, from the reference point, it's nearby the reference point. It's arrows is a bit smaller, and far away is a bit stronger. So I also provide, I mean, how to generate the products with InSAR temperatures analysis, which includes the coherence, temporal and spatial coherence, and the velocity and seasonal subsidence, and the accumulated displacement in each state, the time series. I mean, so we can generate the GeoTIFF folder here, and we can do this step. All right. Okay. And then we can click this folder. Okay, we can see here. This is for example, if the first one is reference data, all the other deformation are relative to the first data. It's accumulated data deformation. We can also save the export the occurrence data, and here is the velocity. And you can see here the gel tips, the coherence, the seeding subsidence, and the velocity, and the temporal coherence. Yeah, and this is the reference from Yunjun. Okay, I think that's all. Thank you.